Hey everyone, and welcome to this episode.
I am absolutely thrilled you're here today because we are looking at something truly foundational. We're going to uncover how a remarkably simple loop of logic gates managed to give digital circuits the one thing they desperately needed to evolve, and that is memory. You see, this isn't just about wires and electricity. It's really the story of how basic circuits went from living only in the present moment to actually being able to remember the past. It's the whole shebang that powers the modern computing world we live in today.
Here's the quick roadmap for our journey today. First, why circuits need memory. Then, we'll meet the S R latch and trace how the latch remembers. After that, we'll venture into the forbidden invalid state. And finally, we'll look at metastability and timing glitches. Let's get into it.
All right, section 1. Why circuits need memory. The limits of basic logic.
Okay, let's dive into this. Before we look at the solution, we kind of have to understand the massive roadblock early computer engineers were facing. Basically, basic combinational circuits are like amnesiacs. They only know what's happening at the exact moment you give them an input. You can't ask them, hey, how many times did this occur? And they absolutely cannot answer the most fundamental question, what happened before? Without memory, any sort of complex digital behavior is just flat out impossible.
Now, what's really interesting about this slide is the clear contrast between these two worlds. Over on the left, we've got our amnesiacs combinational circuits. Their output depends entirely on the current input. Nothing else. But on the right, we see the evolution, sequential circuits. By adding memory and time awareness, we essentially upgrade from simple calculators to the incredible building blocks of modern computing, like CPUs and RAM.
Moving right along to section 2, meet the S R latch, the foundational block of memory. So, how exactly did engineers solve this whole amnesia problem? Well, enter our hero, the sequential circuit known as the latch. Before we peek at its schematic, just notice where latches fit into the broader family tree of memory. Latches are the faster, simpler, level-triggered siblings to edge-triggered flip-flops. They're incredibly efficient, for sure, but as you'll see, their simple design can actually cause some serious, system-crashing timing problems later on. And there it is. This is a clean look at an S R latch built using two cross-coupled NAND gates. Looks kind of like a figure 8, doesn't it? Let's break down these labels. We have two inputs on the left. The top one is S', which stands for low active set. The bottom one is R', or low active reset. Now, because they're low active, that basically means we trigger them by dropping their voltage down to a logical 0. Over on the right, we've got our two outputs, Q and Qn. Now, the absolute golden rule for this circuit is that Q and Qn must normally be exact opposites. If Q is 1, Qn has to be 0, and vice versa. Section 3. How the latch remembers, tracing the logic flow. Now for the really fun part. I want you to follow the ones and zeros through these feedback loops with me. It's honestly like watching a digital brain form a memory right in front of you. Let's trace the set state. We'll start by dropping our top input, S', to 0. Because that top NAND gate receives a 0, it immediately forces its output, Q, to become 1. Now follow that wire diagonally down. The bottom gate now has two 1s as inputs, which forces its output, Qn, to 0. That 0 loops right back up, literally locking the system in place. Boom, we've officially set the latch. But here's the magic question, right? What happens next if we take our finger off that set button? Let's change S' back to a 1. Just notice the truth table on the right. The outputs remain exactly the same. No way, right? When S' changes to 1, that top gate still has that looped 0 coming up from Qn, so its output just stays at 1. The circuit has successfully remembered its state, even after we remove the initial trigger. Let's move on and see how this builds. What if we actually want to clear that memory? Well, we enter the reset state. This time, we pull the bottom input, R' to 0, while keeping S' at 1. That bottom NAND gate reacts to the 0 by forcing Qn to 1. That 1 travels diagonally up to the top gate. The top gate now sees two 1s, so it forces Q to become 0. And just like that, the output has flipped. And, just like before, if we release the reset button by turning R' back to 1, absolutely nothing changes. The bottom gate still sees a 0 coming down from Q, so it holds Qn at 1. The system remembers the reset states. This incredible ability to stably hold either a 1 or a 0 indefinitely is exactly why we call this a bistable circuit. It literally has two stable states of being.
Let's briefly talk about the operation timing of the S R latch.
For our math today, we're assuming a standard uniform gate delay, which we'll just call T. That t just represents the tiny fraction of a second it actually takes for a signal to process through a single gate. This schematic right here is your foundational starting block.
And right here is the normal timing diagram. This is the good stuff, right? Clean, predictable, behaving exactly how the truth table says it should. You drop S prime low, Q goes high after that delay of t. You drop R prime low, Q goes low. When you see this on an exam, these are your safe, easy points. You literally just trace the lines and add your delay t. But hey, we all know exams aren't just about the easy points, are they?
All right, section 4, the forbidden invalid state, breaking the rules of logic.
You know, perfection is kind of an illusion, especially in early engineering. What actually happens if we push this circuit to its absolute breaking point and press both buttons at the exact same time? Well, to understand the danger, we have to clearly define the golden rule we're about to break, the invalidated output requirement. Outputs Q and Qn must be exact opposites. Violating this completely strips away the very meaning of the data you're trying to store.
So let's do it. Let's force both inputs, S prime and R prime, to 0 at the exact same time. Take a look at the circuit trace. Because both NAND gates are receiving a 0, the fundamental physical properties of the gates force both of their outputs to become 1 simultaneously. Q is 1, Qn is 1. The golden rule? Completely destroyed. The system is now in a forbidden state, holding a literal contradiction.
Which brings us to section 5, metastability and timing glitches, a system in chaos.
And this brilliantly illustrates the real danger. Being in the forbidden state is bad enough, for sure, but trying to escape it, that's where things get wild. If we take both inputs from 0 and simultaneously shift them back up to 1, the system completely panics. Both gates are frantically trying to figure out who gets to be a 1 and who has to be a 0. The signals just chase each other endlessly, causing Q and Qn to wildly alternate. This chaotic, unresolvable storm is what we call metastability.
To see just how disastrous this is, let's look at it over time on this timing diagram. We start off perfectly fine, but when S prime and R prime both go from 0 back up to 1 at the exact same time, look at the green lines for Q and Qn. They just start oscillating rapidly. And honestly, the scariest part, we have no idea when it will stop. The oscillation eventually resolves at some unknown point in the future to a completely random state. For predictable computing, having random, uncontrollable memory is just fatal. So the crucial point here is that this metastability isn't just some freak occurrence. It's a built-in physical flaw that can be triggered in 2 main ways. The first is what we literally just saw, both inputs changing from 0 to 1 at the exact same time. But the second trigger is far more insidious, a voltage pulse that is simply too short, specifically shorter than 2 times t. Let's look at what t actually is.
Now, t represents the time it physically takes for an electrical signal to move through one single NAND gate. Because this is a real physical system, electricity is incredibly fast, but it's not instantaneous. To securely set or reset the memory, a signal has to travel through the first gate, output, and then propagate all the way through the second gate to actually lock the loop. That's a minimum of 2 gates, or 2 times t. If you blip the input button faster than 2t, the signal basically gets trapped halfway. And here is that exact glitch caught in action. Check out that first little dip on the yellow S prime line. See how insanely narrow that is? It's way shorter than our 2t window. Since the pulse just disappears way too fast, the green outputs, Q and Qn, literally never get a chance to settle into a stable state. They just freak out and wildly oscillate.
Actually, think about this. When your modern computer or phone completely freezes up and needs a hard reboot, a microscopic glitch just like this is often the culprit behind the scenes.
Thanks for watching. See you next time.